Hi everyone, so this is a video about stability in electrostatics, and the main focus of the video is going to be on the system that I have sketched out here on the screen, where we have got 6 charges, point charges, in an octahedral arrangement at plus or minus a along the 3 Cartesian coordinate axes, and all of the charges that I've drawn have the same charge. Let's just call it Q. Doesn't matter if it's positive or negative. So we're going to imagine taking another point charge, placing it at the origin or very close to the origin of this Cartesian coordinate system. And you can kind of tell by inspection that this is going to be an equilibrium position, because depending on the relative sign of our charge near the origin, compared with the sign of the charges along the axes, either all of the charges along the axes are going to be pulling equally on the charge at the center or pushing away equally. And so if you put it perfectly at the origin, then it's going to sit there. But what's not obvious is whether the equilibrium is stable or unstable to small perturbations. We're going to do the analysis in 3 stages, where we consider adding successive pairs of particles. Firstly, we'll consider the stability of the system that just has the pair of particles at plus or minus a on the x-axis. Then we'll add in the ones along the y-axis, and finally the particles along the z-axis. And we'll come to some hopefully interesting conclusions about those systems, and then turn it into a more general discussion about stability in electrostatics at the end. So let's add in our little test particle, which we said was going to be near the origin. Doesn't matter exactly where. I'm kind of exaggerating the displacement here just so that it's easier to see the diagram clearly. So there's our test particle, and we're going to investigate the stability by figuring out an expression for the electric field due to the 2 point charges which are fixed on the x-axis at the particular position where the test charge happens to be. Now I'm just going to define a couple more parameters in this problem, specifically vectors that are going to make it a little bit more convenient to express the electric field. I'm going to make a relative position vector from the particle on the positive x-axis to our test particle. Let's call that vector r1, and similarly we've got a vector coming from the particle on the negative x-axis to the same position, which we're going to call r2. So we'll express the electric field at the position of the test charge in terms of r1 and r2 first of all. It's also helpful to express those vectors r1 and r2 in component form, so let's do that first of all. So r1 is a vector that goes from a0, 0 to some arbitrary point. Let's just call it x, y, z. Because it goes from a0, 0 to x, y, z, the x-coordinate is just going to be the difference in x-coordinates between those 2 points. So it goes from a to x, so it's x minus a. And then the y and z components are going from 0 to y and from 0 to z. So you've just got y and z as the y and z components of r1. By exactly the same logic, the only difference for r2 is that the starting point is at x equals minus a rather than plus a, so that switches the sign of the a, and we conclude that r2 is just x plus a, and then y and z. So let's write down our first expression for the overall electric field at the point x, y, z. So let's write it down here. Let's call it E. Of course, we've got our prefactor of q over 4 pi epsilon naught, where q is just the charge on each of those charges that we have along the x-axis. Now the electric force is of course an inverse square law type force, and so we're going to have some term which expresses the inverse square distance from both of the original charges on the x-axis to our test charge at x, y, z. I'm going to put a set of square brackets here. Our first term, let's first think about the force from this charge to our test particle. That's going to act in the r1 direction. The inverse square distance between those 2 particles we can write like this. So you've got x minus a squared plus y squared plus z squared. That's just the squared magnitude of the vector r1, therefore the squared distance between those 2 particles. We want to put all of that to the power of minus 1, right? Because that just puts it on the denominator of the fraction. It's an inverse square law. And then we put our vector r1 here, because this is a vector expression and that electric field acts in the r1 direction. However, there's one other little correction we have to make to this, which is to remember that r1 is not a unit vector. So this R1 here doesn't just contribute a direction, it also affects the magnitude. So we have to divide one more time by the magnitude of R1, which is basically all of this stuff to the power of a half, right? So overall, your power here is going to be -1.5 or -3/2. And then by exactly the same logic, you're going to have a very similar looking term for the force or the field due to the particle along the negative x-axis. But this time you're just going to have a plus in front of the a. So x plus a squared plus y squared plus z squared, then all to the -3/2, and then that's proportional to the vector r2. So this is a general expression for the electric field at position x, y, z. However, of course, it's not the nicest looking expression, and if all we're investigating is stability, we don't really need an exact expression, we just need an expression that tells us what the electric field looks like for very small displacements. So we can do some approximation, do a binomial expansion on some of the terms here to get a first order approximation for the electric field. So specifically, let's just focus on the term x minus a squared plus y squared plus z squared, all to the power of -3/2. So if we want a first order approximation of that, we just want to expand it as much as possible to start with. Firstly, we can already neglect the y squared and the z squared because they're second order terms. When we expand the squared bracket, we're going to get an x squared as well, which we will be able to neglect. You're also going to get an a squared and a -2ax, however, which are 0th order and first order terms in terms of x, y, and z. So this is approximately equal to just a squared minus 2ax to the -3/2. If we want to do a binomial expansion, it's easiest if we make sure that first term is 1, so we can factor out that a squared. When we apply the power of -3/2 to the a squared, it becomes a to the -3 out in front. Then you're going to have 1 minus 2x over a after that's been factored out, still to the power of -3/2. And then we can keep that a to the -3 there, and we get 1 plus, basically you just have to do -2x over a times -3/2, which is 1 plus 3x over a, and I'm ignoring quadratic order terms and higher. So this is a first order approximation for that term. So let's turn that into sort of an approximation for the full electric field expression that we have down at the bottom left. So I say therefore our electric field E is approximately equal to, well, we've got our Q over 4 pi epsilon naught, but if you look at this term here and this term here, they only differ by the sign of A. So the expression that we're going to get for our first order approximation for each of those is going to be pretty similar, other than sort of just differing by a sign. In particular, they're both going to have this a to the -3 as a prefactor. So we may as well take that out as a prefactor of the whole thing and put an a cubed on the denominator there. Then substituting in our approximations, we have this 1 plus 3x over a, that's coming from this approximation that we just did, times the vector r1, but we already know the vector r1 is that stuff. So let's write that in as a column vector, x minus a, y, z, then plus our other term. Well, we don't have to go through the full process to approximate that because, again, look back at this approximation here, going from that to this, the only difference that the x plus a squared term would have is that sign there would be a plus, and therefore this sign there would be a plus, and that would follow through to make this sign here in the final approximation a minus. So if we just get rid of some of those annotations, we can write in then 1 minus 3x over a, and then our r2 vector, which we had up here, again, just differs by a sign. So x plus a, and then y, z. There is a first order, well, not quite, but getting towards a first order approximation for the electric field. I say not quite because there's still some more terms that we can ignore when we expand out some of those brackets. So let's see how that works. This is approximately q over 4 pi epsilon naught a cubed, same prefactor. If we, well, let's just turn this into one big column vector now and multiply out some of these brackets. So our x component, you're going to get from this first term, you're going to get 1 plus 3x over a times x minus a. So that's going to contribute, when you do the 1 times this stuff, you're going to get x minus a. That's all first order or 0th order, you're going to get a second order term that you can ignore, right? You're going to get that times that. That's going to be an x squared term. Let's ignore that. However, this times this, we need to keep. That's minus 3x. How about for, well, the contribution that you get from that second term? Pretty much the same logic. You're going to get x plus a. You ignore the x squared term, and then you get minus 3x as well. So the minus a and the plus a cancel out, and that x component simplifies to just minus 4x, which is nice. What about the y and z components? Well, you get 1 times y, which is just y. You get 3x over a times y. That's a term which is proportional to xy, which is a second order term, so let's ignore that. Similarly, from this bit over here, you get your 1 times y, which is another y, but you ignore your xy term. So overall, you have 2 y's, and the z term is exactly the same. You just got 2z there. So if we just tidy this up, take out an extra factor of 2 from the individual components in the vector, your prefactor is now q over 2 pi epsilon naught a cubed. Then you've just got minus 2x and then y and then z. So just to summarize, I've kept our first order approximation to the electric field here. I've called it E subscript x, meaning the electric field due purely to the charges on the x-axis, because remember later on we're going to add charges along the y-axis and z-axis as well. But what does this imply about the stability? So let's just assume for the time being that our test charge, remember, which was this little cross in the diagram up there, let's assume the test charge has the same sign as the capital Q charges along the x-axis. Then the force, the electric force, will have the same sign as the electric field. And so you can see that just looking at this bit here, when x is positive, the x component is negative, and therefore if you pull your like charged particle a little bit purely along the x-axis, it's going to be pulled back to where it started because the force is in the opposite direction to the displacement. So that implies that your particle is stable to perturbations which act purely along the x-axis, right? Assuming that the y and z components are 0. The opposite can be said for displacements in the y and z directions for the same reason. So those are going to be unstable because if you displace your particle a little bit just along the y-axis or just along the z-axis or along some combination of both, then your force is going to be positive. It's going to be pushing away from the x-axis, and your particle won't be pulled back to its equilibrium. So the stability of our particle depends on which direction we perturb it in. Of course, if you flip the sign of your test charge, then those conclusions are reversed. It would be unstable to perturbations in the x direction, but stable to perturbations in the y and the z direction. And that's pretty intuitive. For the rest of this video, I'm going to sort of by default talk as if the test charge definitely has the same charge as the ones along the axis, but always keep in mind that the conclusions would just be exactly the opposite if we were considering a charge of opposite side. So that's all good and seems to make physical sense. So let's add to the complexity of our system and put in some more of the charges that we originally had. So we're going to have charges along the y-axis, one at minus a over there, and one at positive a. And let's come up with the first order approximation for E. I'm going to call it EXY, meaning electric field, due to the particles along both the x-axis and the y-axis. Now we can actually get that very quickly just by inspecting what we've got for this EX down here. So the way that works is we're going to keep the same prefactor Q over 2 pi epsilon naught a cubed. Keep the contribution that we've already got, so minus 2x and then y and then z. And we're going to add on another contribution. Now, the idea is that physically there's no difference between the x-axis and the y-axis, right? It's just the way you label it. So you would expect, if you went through all of the same analysis, you would expect to get a very similar looking electric field vector due to the particles along the y-axis, but the components would be flipped around, right? You're basically not changing the meaning of z, but you're switching the meaning of x and y. So that means your x component is just going to be x because the y component of the original vector was just y. and the y component of the new vector is going to be minus 2y, because that was sort of the x component of the original vector, and z, as we said, is just still going to be z. Just a neat little symmetry argument we can use there to save doing some more algebra and binomial expansions. And if we go ahead and simplify this, you've got q over 2 pi epsilon naught a cubed. Your vector term here is now minus x and minus y and 2z. By the same logic as before, we can just look at the signs here and use those to deduce things about stability and instability. The first two components, x and y, are negative. That means your particle is going to be stable. Let's put S for stable, to perturbations in the x and or y direction, but still unstable in the z direction. Again, this makes a lot of sense because if you imagine a particle, you've got this sort of square planar arrangement in the xy plane of 4 charges. You start with a test particle in the middle, you push it up a little bit, and all of the charged particles in the xy plane are just going to be pushing it up. There's no way it's going to be pulled back to equilibrium along the z-axis, but if you displace it a little bit within that xy plane, then it's going to be pushed back to the center. So it does kind of look as if we've, in a certain sense, fixed some of the instability, right? By adding an extra pair of particles along the y-axis, we have turned the perturbations in the y direction from initially unstable to now stable. Again, that kind of makes sense. And so we might naturally think that if we put another pair of particles along the z-axis, then it's going to fix the z stability, the z instability as well. So let's investigate that. So let's put a particle back up here at z equals a, and another particle down here at z equals minus a. Now you've got your full octahedral arrangement of charged particles, and I'm going to call the overall electric field E x, y, z. So we can use a similar method to what we did before. Start with what we've already got. So we've already got minus x, minus y, and 2z. If we look back at our original EX vector, again, we just used the symmetry to figure out what the contribution to the electric field by the charges along the z-axis is going to be. Originally, x was like the special direction. Now z is the special direction. So instead of minus 2x, y, z, you'd expect to have x, y, and then minus 2z. So I'm going to add on x, y, and minus 2z. Then something interesting happens, because if you look at what you get when you add the vectors together, you just get 0. So that suggests that your electric field is the 0 vector. Now this might seem a bit strange at first, but it's not wrong. It's just not very helpful, right? This is just saying the electric field is 0. This is fine. It just means that there is an equilibrium position at the origin. But what this is telling us is that a first order approximation is not good enough to tell us about the stability, right? The first order terms have actually cancelled out. So we would need a higher order approximation to this total electric field if we want to investigate the stability. So I took some time to do a higher order approximation, did the binomial approximation to third order, and came up with this big vector expression that I've written at the bottom there. I've said, hopefully, because it's very easy to make mistakes with this sort of thing, I've checked my working a couple of times and I couldn't find any, but I don't have any reference that I can check against or anything. So if anyone's interested in having a go at doing the approximation yourself and telling me if you get the same thing, that would be interesting, but it's not the most fun exercise. I just sort of extended the method that we were doing earlier. Looking at this, there's a certain nice symmetry about it, and so I do feel like there might be some clever trick you can do with coordinate transformation or something, but let's just assume that this is correct for the rest of the video. So what can we conclude about the stability of the system from this electric field? Well, let's consider stability in a couple of specific directions. So what I mean by that is, firstly, let's just suppose that your displacement xyz is in the x direction. In other words, xyz is some small value epsilon, not related to epsilon naught up here, but just some small value, and then 0 and 0 in the y and z directions. So if you go through and substitute those values in there into this big vector, everything involving y and z disappears. So the y and z components of the overall vector disappear, and you're just left with, up to a constant, your overall electric field will be proportional 2 minus epsilon cubed coming from this term here, and then 0, 0. So when epsilon, the x displacement, is positive, then the force, the resultant force, is negative, and vice versa, which suggests that our system is stable to perturbations in the x direction, which again makes sense because you've still got those two particles on the x-axis pushing the particle in the middle away. Then it turns out that, well, unsurprisingly, really, you get similar results by symmetry if you consider the vectors 0, epsilon, 0, and 0, 0, epsilon. You get like a version of this vector here, but with the minus epsilon cubed in a different position. So it's stable to perturbations in the x direction and the y direction and the z direction, but that doesn't mean that it's stable to perturbations in every direction. And the reason is because you have all of these mixed terms in your vector over here. It's not just sort of x's and y's and z's separately. You've got terms that mix together every possible combination of x, y, and z, right? So it is plausible that we could find a direction in which the perturbations are unstable. An example of that would be considering the vector, so x, y, z, being, well, equal small displacements in all directions. So epsilon, epsilon, epsilon. You go through that and you find that your electric field vector is proportional to epsilon cubed in the x direction and in the y direction and in the z direction as well. So when epsilon is positive, that means a small positive displacement in all directions gives you a small positive force in all directions. That means the system is unstable to perturbations in the sort of 1, 1, 1 direction. So even though we've sort of fixed the instability in all three directions, x, y, and z, we can't escape. It seems that we can't escape having some direction in which the perturbations are unstable. So what if we take this idea to its extreme and try to fix the instability in every possible direction? Is that possible? So what you would end up doing is basically making a sphere, right? Because if you add a pair of charges, as we've done on each of the three Cartesian axes, if you add a pair of opposing charges, I don't mean opposite signs of charge, but opposing spatially. If you add a pair of charges in every possible direction, you're basically filling out a spherical shell of radius a. So your geometry would not really look like this octahedron up here, but you would just have a sphere. And it's a well-known result that in electrostatics, if you have a sphere of charge, you can show this from Gauss's law, or using other arguments about inverse square laws, but you have zero electric field in there. So if you try to take this idea to its extreme and make every direction stable, you kind of succeed in the sense that you get rid of the instability, but now you don't have an equilibrium at all, right? There is no electric force at all inside that shell, which is interesting. So what's actually going on here? What's the deep reason behind all of this? Well, it turns out that you can explain this quite neatly using one of Maxwell's equations in free space, which is that the divergence of the electric fields in electrostatics is 0. In free space, therefore there's no source term on the right-hand side, it's just 0. So the electric field doesn't have any divergence. If it doesn't have any divergence, that means it doesn't have a net flux through any given closed surface. Now, if you want to have a stable equilibrium position, then let's say your desired stable equilibrium position is this dot over here. You would need to have every direction of displacement giving you a force that acts straight back where you came from, or equivalently, an electric field vector that points straight back where you came from. However, this kind of arrangement is just not possible if you have a divergence-free field. The electric field arrows would have to sort of go in one side and come out the other side if there's to be no net flux to the surface, right? Imagine a little spherical surface there, for example. All of the electric field arrows, if you wanted to have a stable equilibrium, would have to be pointing inwards, but that contradicts Maxwell's equation here. So this is not possible in electrostatics at all, which is kind of an interesting result. Anyway, I think let's leave it there for today. Hope this has been an interesting look at stability. Let me know if any of you decide to try and verify my third order electric field approximation, and I'll see you again soon.